So is my slides visible to everyone? Hello?
Yes, sir.
Okay. All right. So first of all, thank you for coming on Sunday. Let us start with what we have covered in the last class. So in the last class, we started looking at the basic concepts of radiation. Okay. So the argument we have given is, so far we have covered the conduction, then we have covered the convection, and the last mode of heat transfer that was remaining was the radiation. So that's why we started with the radiation. Again, we started with a very simple, basic concepts which you have already done in your JE days, but just for a sake of, completeness and continuity, we are doing it again. So we said that we have initially, defined this different terms we have, discussed, like transmissivity, emissivity, reflectivity, uh, and absorptivity. These we have defined initially. Then we have started looking at the concept of black body, and then we started looking at different laws. So the first law we have started is the Planck's law. So Planck's law says the monochromatic emissive power or a spectral emissive power of a black body is a function of wavelength of radiation. So since we are saying monochromatic or spectral emissive power, that's why this E is having a subscript B and lambda. So here B denotes to black body and lambda denotes to the particular wavelength. Okay. So based on this law, this EB lambda is related to lambda. That's what we have seen. So in this particular equation, if we put all other constants, we get this equation k1 lambda raised to the power minus 5 divided by exponential of k2 divided by lambda t minus 1. Here k1 and k2 we can calculate here as given. So now based on the Planck's law, we said that so if you plot the spectral emissive power with respect to wavelength, a typical distribution we get is as shown here. So depending on the temperature, the peak of this particular plot is going to move from right to left. So if the temperature is low, in that case the peak will be somewhere in the right hand side, whereas when the temperature is very high, in that case the peak will be at the left hand side. Why? Because we are saying that uh, all the objects are going to emit the radiation in all wavelengths from 0 to infinity, but the energy dependent on the fact that at which particular wavelength most of their radiations are concentrating. Okay, and the lower is the wavelength, higher is the energy, isn't it? So in all these plots, you can see that all these plots are varying between 0 to infinity, but their peak is varying at different locations, isn't it? So the lower temperature objects are emitting at a higher wavelength, whereas the higher temperature objects are emitting the emissions at lower wavelength. Okay, so this is what we have seen initially. Then we said uh, since all these emissions are going to, the distribution of these emissions are going to have a peak, and that peak is located at a particular value of lambda, isn't it? So is there any way we can quantify that? So there this another law comes into the picture, and which is nothing but Wien's displacement law. So Wien's displacement law says uh, at the peak of EB lambda versus lambda plot, lambda max into T is a constant. So this is a constant value, doesn't matter what temperature we are looking at. So lambda max into T is a constant. So clearly as temperature increases, lambda is going to decrease. Okay, so this lambda max into T, so lambda max is nothing but the value of wavelength at maximum spectral emissive power in this particular plot. So wherever the maxima is occurring, that particular wavelength is called as a lambda max. Okay. So far we were talking about the spectral emissive power only, but as we have discussed that the emissions will be emitted in all wavelengths from 0 to infinity, we need to account their entire effect, isn't it? So there comes another law, which is nothing but a Stefan-Boltzmann law. In a Stefan-Boltzmann law, we are calculating the total emissive power instead of calculating the spectral emissive power, which is we have earlier obtained using the Planck's law. So in this case, this EB lambda, which is nothing but the spectral emissive power, is integrated over the entire range of wavelength from 0 to infinity. Okay, so after doing this integration, here you can see this integration is slightly complicated because here this typical mathematical functions like gamma function etc. are coming into the picture. So but finally you will see that this total emissive power of a black body comes out to be sigma into T raised to the power 4. So Stefan-Boltzmann law is stated as the total emissive power of the black body is proportional to the fourth power of absolute temperature, and the proportionality constant is a Stefan-Boltzmann constant, which can be calculated as 5.669 to 10 raised to power minus 8 watt per meter square per Kelvin raised to the power 4. Is it clear to everyone? Up to this we have done in the last class. Hello?
Yes, sir.
Okay. So now, so in this case, we have just looked at how the total emissive power of the black body we can calculate. But very often we are not interested in calculating the total emissive power. Rather, we are interested in finding how much will be the radiation between a particular wavelength. For instance, I might be interested in finding out the total amount of radiation between 0 and lambda, where lambda is not infinity, it's a finite value, isn't it? So in such cases, there is another term which is used regularly, which is called as a fraction. So fraction FB 0 lambda is nothing but the fraction of the radiation falling in the wavelength range between 0 and lambda divided by the total emissive power. So this is nothing but the ratio of the radiation between 0 and lambda divided by radiation between 0 and infinity. Okay, so this is defined as the ratio of emissive power between 0 and lambda and emissive power between 0 and infinity, where wavelength is varying between 0 and infinity. So we can define this FB factor as FB factor between the range 0 and lambda as given here, and this is defined as the integration of 0 to lambda EB lambda d lambda. So this numerator is going to give me how much is the amount of radiation present in the wavelength range 0 to lambda, and divided by the total emissive power. So total emissive power, again we can get it by integrating the spectral emissive power over the entire range of the wavelength between 0 to infinity. So this total emissive power here is given as EB lambda d lambda integration between 0 to infinity. So this we have already calculated, isn't it? This we have already calculated as sigma into T raised to the power 4. So we can directly put it here. Okay. Whereas this numerator, we can represent EB lambda using the Planck's law. So that is given as K1 lambda raised to the power minus 5 divided by exponential of K2 divided by lambda T minus 1 d lambda. Is it clear to everyone? Equation number 6.
Yes, sir.
And what is the relevance of equation number 6 is clear to everyone. Why we are defining this F factor, a fraction. Is it clear or not clear? We are defining this term because very often we are not interested in finding the total emissive power. We are interested in finding the emissive power between a particular wavelength, isn't it? So can I get a fraction of emissive power between a particular wavelength divided by a total emissive power? That particular quantity is defined as F factor. Okay. So again, in this case, 1 by sigma T raised to the power 4 is there. So this T raised to the power 4 we can take inside this function. So that will become K1 divided by lambda T raised to the power 5. And this d lambda again we can we can have lambda T here inside. So you can see all these the T raised to the power 4 terms which are there outside the integral can be substituted here inside the function. So after substituting, we get a very good nice function like 1 by sigma integral between 0 to lambda t k1 lambda t raised to the power minus 5 divided by exponential of k2 lambda t minus 1 d lambda t. Now here you can put this lambda t as another variable y or x and you can integrate. So your integration becomes easy, isn't it? Do you all agree?
Yes, sir.
But the only problem is, again, see, remember the similar expression we have seen in an earlier slide. We got the similar expression here, isn't it? And that leads to a complicated gamma function, isn't it? So very often, instead of solving this gamma function again and again, what people have done is they have reported the values of this f factor. They have reported the values of this f factor with respect to this lambda t. Remember, in this entire equation, the lambda t is the variable. Can you see the point here? Here in this entire equation, lambda t is the variable. So how my f factor is going to vary with respect to lambda t, that is tabulated. So most of these heat transfer book, you will see this table. This is because it is going to help you solve the problem easily instead of doing a analytical calculation of this complicated gamma function as shown here, isn't it? Instead of doing that, we can directly go to this table, find out lambda t first, and corresponding to this lambda t, we can find out the f factor. So if you look at this f factor, the range of this f factor is varying between 0 and 1. So when lambda t is 0, in that case f factor is 0. When lambda t is infinity, in that case f factor is 1. So this f factor is varying in the range 0 to 1. Okay. Is it clear to everyone why we have tabulated all these values here?
For the values of lambda t in between, we have to just
do the
linear
interpolation, a linear interpolation, you do it and then you use those values. Absolutely. So you will not get a pinpointed values here in this table, isn't it? But you can interpolate linear interpolation you can use and find out the corresponding f factor. So take a typical example here. Okay, we will see that. Okay, so here f factor you can find out. Very often another question is asked, and that another question is, in this particular case, we have looked at how much fraction of radiation will be falling between 0 and lambda. But let's see if I ask you another question, how much is the fraction of radiation falling in the range of lambda 1 to lambda 2? So instead of starting from 0, I am starting from lambda 1 and I'm ending at lambda 2. So this original equation we can represent for such cases. So FB factor between lambda 1 and lambda 2 can be represented as again 1 by sigma integral lambda 1 t to lambda 2 t k1 lambda t raised to the power minus 5 divided by exponential of k2 lambda t minus 1 d lambda t. So only difference here is these limits we have changed from lambda 1 t to lambda 2 t, isn't it? So again this new equation we can represent as the integral between 0 to lambda 2t minus integral between 0 to lambda 1t, isn't it? We can write down that. Yes or no?
Yes, sir. Yes, sir.
So that means it is going to give me the subtraction of two f factors, isn't it? We can have the subtraction of two f factors, and that's what is shown in this equation, isn't it? So we can write down this equation itself as this equation we can write down as 1 by sigma integral of 0 to lambda t and this entire bracket. Correct. Minus 1 by sigma 0 to lambda 1 t and again this entire bracket, isn't it? So these two terms are nothing but what? These are this term, isn't it? Does it make sense to everyone? Correct.
Yes, sir.
So again, in this case, if we look at the starting from zero, if you are, let's say if you are putting lambda 1 equals to 0, in that case this f factor will be what? Lambda 1 is 0. That means lambda T is going to be 0 and therefore corresponding F factor will be 0. So you will get FB 0 to lambda 2, isn't it? So you can get it directly. You can get this original equation from this. Okay, so the point we wanted to make here is very often we are interested in finding out the radiation within the given range. For instance, so let's take this simple example which we are repeating again and again. So you can see that the temperature of the sun is 5780 and we said that the visible range of the radiation from the sun is between lambda 1 equals to 0.4 and lambda 2 equals to 0.7. So we wanted to find out how much is the fraction of radiation between these two wavelength ranges. What is the fraction of radiation between this range of wavelength, isn't it? Lambda 1 to lambda 2. So now in this case, lambda 1 is 0.4 and this temperature is already we know 5780. So lambda 1 T we can find out, that is 2312. We can find out that 2312 here in between these two. So we can interpolate it, isn't it? And we can find out the corresponding F factor. So corresponding F factor comes out to be 0.1229. 0.1229, that is what you are going to get it here somewhere middle. Okay, clear? Similarly, lambda 2 is 0.7. So it is 0.7 we can multiply to a temperature of 5780. We will get 4046. So that is somewhere here 4046. Again we can interpolate and we can find out the corresponding value of F factor. So that is comes around 0.4889. And the subtraction of these two values comes out to be 0.366. So what this value is giving me the information? This value gives me the information that almost 36.6% of the total radiation from the sun falls into this visible range. Correct? That's a significant fraction. That's a significant fraction concentrating only in the small region. Only in this small region which we are showing here. Only in this small region. Okay. Even though all the radiations are starting from here infinity, 0 to infinity, but most of these are falling only in this small region which is shown by a strip here. And therefore the sun appears bright. Okay. Is it clear to everyone?
Yes, sir.
My slides are visible to everyone? Hello?
Yes, sir. Yes, sir.
Okay. Okay. So the point I'm trying to make it here is if any questions are there on this particular topic, you refer to this table and find out the values. Don't do this complicated analytical, mathematics, which is shown here. Okay. So this is only given here just to appreciate the concept. Okay. But for actual calculation, you go back to this table and find out the corresponding values using linear interpolation and use those values in calculations instead of doing instead of solving this particular integral analytically. Is it clear? Is it clear to everyone?
Yes,
So
sir.
this table is given in almost all the heat transfer books. It is given in the book which we are referring. Also in, if you look at any book on heat transfer, you will see this table. Can we move ahead? Hello, is it clear to everyone?
Yes, sir.
So the last law in terms of basics is the Kirchhoff's law. So what Kirchhoff's law is saying is when a body is in equilibrium with its surrounding, its absorptivity is equal to its emissivity. That's what we have to prove. So let's look at the body 1. So rate at which the body 1 is going to emit the radiant energy will be what? Its emissive power multiplied by area, isn't it? So E1 into A1 will be the rate at which the body 1 emits the radiant energy. Okay. Again, the rate at which body 1 is going to receive the radiant energy will be what? So Q is the amount of heat coming in, that multiplied by area A1, isn't it? will be the amount of heat coming in towards the surface 1, but only the fraction of that is going to get absorbed, and therefore absorptivity should be multiplied here. So the rate at which the body 1 receives the radiant energy will be given by alpha 1 Q into A1, isn't it? And both these factors should be same at the equilibrium, isn't it? Then and then only the temperature of the body will remain at a constant value. Otherwise, the temperature of the body will increase, isn't it? So when we are saying that a particular body 1 is in equilibrium with the surrounding, that means its temperature is not varying. So amount of energy it is emitting should be same as amount of energy it is absorbing, isn't it? So at equilibrium, at thermal equilibrium, both these factors should be equal to each other. So this A1 will get cancelled out. What we will get is E1 is given as A1Q. Okay. Now this is for any body. This is for any body. Okay. But if we write this equation for a black body, this particular equation is for any body. But this equation, if we write for a black body, what that equation will be? For a black body, this alpha 1 is just 1, isn't it? So EB will be given as just Q, isn't it? For a black body, this earlier equation, this E1 equals to alpha 1 Q, this is going to change. This E1 equals to alpha 1 Q, this is true for any body. But for a black body, it will be EB is given as Q. So if I divide both these equations, what I'm going to get? E1 by EB. E1 by EB is given as alpha 1. Isn't it? But E1 by EB is what? Emissive power of any body divided by emissive power of a black body, that is nothing but a emissivity. Isn't it? So E1 by EB is nothing but emissivity E1, epsilon 1. So alpha 1 equals to epsilon 1. That proves the Kirchhoff's law. So Kirchhoff's law is saying that the emissivity of a body which is in thermal equilibrium with its surrounding is equals to its absorptivity. So these are the basic laws in the radiation. Okay, this up to this you all might have seen in your JEE days. Okay, now let's look at some more complications. Up to this everything was normal. This you have already done in your preparation, JEE preparation, or otherwise in the first year physics maybe. Now let's try to add some complications based on the real life applications. So far we were only looking at the black body. We were assuming everything, very good, isn't it? But that's not true in a real application, isn't it? So let me share another file where we will start adding more realistic, concepts in this radiation. Okay. Is my new file visible to everyone?
Yes,
Yes, sir.
Okay. So up to this we were saying that everything is okay. Now let's start adding some complications. So the first complication is the directional nature of the thermal radiation. And why we are interested in directional nature of the thermal radiation? In the last slide, we were saying that the emissive power is directly given as what? Sigma into T raised to power 4, isn't it? If it is a black body. If it is any general body, how we calculate it as? Emissivity multiplied by sigma into T raised to the power 4. That's how you will calculate. Do you agree with me?
yes, sir.
Yes, sir.
Maybe I write. Okay. So that the context will be clear to you. Okay. So in earlier slide, we said that emissive power for any body, it need not be a black body, can be given by what? Can be given by its emissivity into sigma into T raised to the power 4. Do you all agree? That's what we have seen in the last slide, isn't it? But it is not complete truth. It's not a complete truth. Why? Because this particular expression is assuming that this particular expression is assuming that all the radiation which are there surrounding this body are absorbed by this particular body. That's not true. That's not true. So for instance, if you look at this differential area A1 and there is another differential area, let's say A2, if I am interested in finding out how much the radiation, how much radiation emitted by DA1 is absorbed by A2, isn't it? Absorbed by A2, that heavily depends on this particular angle, this particular solid angle. Okay, so basically it depends on what? It depends on, so see, if you are looking at from this entire periphery of this area A2, if you start looking at DA1, how much solid angle is subtended by A2 at A1, that defines how much radiation emitted by DA1 will be actually received by A2, isn't it? This DA1 is going to emit the radiation in all direction in this hemisphere. DA1 is going to emit radiation in all direction in this entire hemisphere, but only the part of that emissions will be intercepted by A2, isn't it? Do you agree with me?
Yes, sir. This this solid angle concept will be useful when we are talking about the how much radiation is absorbed by a body, not about how much it has emitted.
No, okay, all right, I understood. Okay, I'll give you another perspective in that. Okay, so very often what we do, we try to find out the equilibrium between different surfaces. I agree with your point that when we are looking at the radiation or emission, in that case this particular thing will not come. That's what you are trying to say, isn't it? The solid angle will not come. That's what you are saying. But the point is, the temperature of this body, depends on how much radiations are received from this DA1 to A2. So even though it's not directly coming out, but that temperature depends on that. Because of that, this concept is also coming into the picture. Is it clear? Still not clear?
Is it like that I have a body, let's say Earth, and the radiation is coming from sun. Now that sun's radiation will increase the temperature on the surface of the Earth, which will eventually lead to the increase in the emissivity of the Earth. Like that.
I'm trying to say this. See, sun is emitting the radiation in all direction, isn't it?
Yes, sir.
Sun is emitting the radiation in all direction, but the solid angle with which the radiations are approaching towards the Earth, only those radiations will be absorbed on the Earth, isn't it? And only those radiation will be responsible for the increase in the temperature, isn't it? So how much radiation will be emitted by Earth also depends on how much is the temperature of the Earth, and that temperature of the Earth it also depends on how much radiation you are intercepting from the sun. Because very often we are looking at the things in a equilibrium, isn't it?
Yes, sir. Yes, sir.
So when such situations are there, in such cases, this solid angle will lead to another factor which is called as a view factor. View factor or the shape factor. These are the different terms used in different books, but both are same. Some people call it as a view factor, some people call it as a shape factor. So that shape factor depends on this solid angle. So in addition to this epsilon, there will also be a shape factor coming into the picture. Does it make sense now?
Yeah. For Earth, it would be a disk receiving radiation.
And very often, see, again, another important thing is very often we are not interested in how much is the radiation coming out from the particular object. Very often we are interested in what is the difference in the radiation between the two objects. isn't it? Remember in the starting slide itself, I said that both the bodies are radiating, but the net radiative heat transfer depends on the subtraction of these two. So very often we are interested in net radiative heat transfer instead of just looking at the radiation itself. Got the point? And there this factor, this particular solid angle or the view factor or a shape factor also comes into the picture. In fact, you will get a better clarity in a subsequent slide. Is it okay?
Yes.
What we are trying to appreciate at this slide is it's not that just the emissivity is important in the radiation, also a solid angle, which will be intercepted by a one body on the other is also important. So in this case, what we are saying that since this differential area dA1 is emitting in all this direction in this hemisphere, but only the part of that will be intercepted by A2, and that part of that intercepted by A2 is this is accounted through a solid angle, and this solid angle is defined as the solid angle subtended by the area A2 at the differential area dA1 is numerically equal to the area A of the portion of the sphere of radius with center at dA1 here, which is cut out by a conical surface.
Sir, slides are not shared if you are reading
Yes.
from the slides.
From just now or
Just now.
Like, when you were explaining now, so that what won't require slide, but now it's requiring because you are like.
Okay, all right. I thought my slides are visible. Sorry. Okay. Is it visible now?
Yes, sir.
Okay, so what I was trying to say here is, so we are having, let's say, a differential surface area dA1. This differential surface area dA1 is there. There is another surface area A2. We are interested in finding out the heat transfer between these two surfaces, A1 and dA1 and A2. Okay. Now in this case, this dA1, if you look at dA1, this dA1 is going to emit the radiation in all direction, isn't it? In this case, we will have to consider a hemisphere, because that will be the half of the sphere which is, in which these radiations are emitted, isn't it? And only the part of that will be intercepted by A2, isn't it? And how we are accounting that? We are accounting that through a solid angle, and this solid angle is defined by, it is numerically equal to a area of the portion of the sphere. Remember, at this point, I can draw a sphere with the radius of R with the center here at dA1, but that radius should be equals to 1 unit radius. Okay. So area A of the portion of the sphere of unit radius with center at dA1, which is cut out by a conical surface with a vertex at dA1 passing through the perimeter of A2. So what we are going to do is we are going to draw a conical, or depending on whether this particular area is circular or not. Depending on that, we will have a solid angle which is intercepting this entire periphery of the surface A2. But the actual solid angle which is taken in the calculation is this, which is shown by the red circle here. So this red circle is nothing but if I draw a sphere around this with the radius R equals to 1, that sphere will exactly pass through this particular red sphere, red circle here. Okay. Is it clear to everyone? So actually the solid angle will be this complete angle, but in the calculation we take the solid angle only at R equals to 1. We don't take it at this actual R. So actual R could be more than 1, isn't it, up to this? But we take the solid angle only at R equals to 1. So numerically it is defined by this equation. Numerically, if you define the solid angle, is defined as W. W is given as, sorry. So omega, numerically it is defined as omega is given as whatever the area I am going to have here, A by R square. That's how it is defined. So in this case, R is 1, so this will be just A. Okay. Is it clear to everyone? So there are 2-3 things why we have taken a hemisphere. Is it clear to everyone why we have taken a hemisphere?
Hello.
Hello.
Sir, I had a doubt that if the real radius is less than 1, then what we will take?
We will take it beyond that.
Okay.
Isn't it? I can extend this further, isn't it? You can extend it further here, isn't it? Doesn't matter. Correct?
The solid angle won't depend upon the radius, whatever you take.
No. So in this case, yes. So we are taking A by R square, where R we will take it as a unit. So that will be A by. So in a way, why this unit radius we are saying is so that we can get it in terms of area. We will get it in terms of area, even though the unit of this W is steradian. Is it clear?
Yes, sir, I got it. We have to get the area at the unit distance.
Unit distance, correct. So actual unit is a steradian, but you will get in terms of area by taking this radius equals to 1. So that simplifies mathematical calculation later on. That is why it is defined like this. Is it clear to everyone? Does it make sense?
Yes, sir.
Okay, so another question which I was saying, why we have taken this hemisphere here? Anyone? Is my slides visible? Is my slides visible? Okay. Why we have taken this hemisphere?
All
There
the
are
radiation would
small
be
details are there. Why I'm asking this question is because there are small details are there.
The normal vector is parallel to the vector that will be there for the area.
Okay. So
at every direction.
Okay. So ultimately any body will be emitting the radiation in all direction, isn't it? Correct?
Sir, but that depends upon the source. If source is like a point object, then it will be a like symmetrical, spherical. If it will be a linear object,
even if you take a Earth will emit the radiation in all directions, isn't it?
Yes, sir. Spherical objects will do like that, but a linear object may be like, so that will emit like a cylinder.
Even you take this cup, this will also emit in all direction.
But sir, not readily out, like they will be randomly in any direction.
No. So see, we are not talking about the intensity or anything. We are saying only a simple thing, whether these are going to emit in all direction or not.
Yeah, that is true. Direction, like there is no difference.
They are going to emit in all the directions, right? Correct. So that means actually we should consider a sphere, but just to ease out the calculation here, the hemisphere is taken. So half, remember this part is above here. So we are assuming that below there is nothing is happening. Okay. So even if you are solving for a half sphere, you can extend it for a full sphere also without any problem. That's what we are trying to do, isn't it? That's why in radiation you will see that most of these quantities are defined in terms of hemisphere. So you will have the quantities like hemispherical, spectral intensity, hemispherical spectral emissive power. This type of terms are there. So these are terms defined only for the hemisphere. That means half sphere. Okay, is it clear? The only rationale behind this entire thing is the radiations are going to be emitted in all directions. in all directions. That is what the rationale is. Correct. So here we are. You may ask me that why we are not consider A2 in all direction. We are interested in finding out how much the radiation emitted from A1 will be intercepted by A2. But if I ask a reverse question, how much is the fraction of A2 radiation emitted from A2 is intercepted by DA1? In that case, I would have taken A2 here and DA1 somewhere else. Isn't it? Does it make sense to everyone? We are asking that what is the fraction of radiation emitted from DA1 will be intercepted by A2. That is what the question we are trying to answer here. But if I ask a reverse question, how much is the fraction of radiation emitted by A2 are intercepted by DA1? Then I will be interested in finding out the solid angle subtended by A1,
DA1
on 2. A1
Yes,
at
sir.
A2. Correct. Again, why we have taken DA1 here and not A1?
Sir,
Why we have
because
taken a differential element here?
sir, because for conical that would be a tip. Like, sir,
Okay,
it
so
has
the
to be
point here
very
is
small.
okay. So point here is see this DA1. This solid angle depends on what surface area you are having, isn't it? Whether it's a conical, whether it's a point source, or whether it's a spherical, or whether it's a cup shaped. Even though these are emitting in all the directions, but this solid angle depends on this, isn't it? Correct. So that's why in order to get the complete picture, we have started with the assumption of elementary point here, and this we are going to integrate over the surface. That's why DA1 is here. Later on, you will see that whenever we are having a DA1, we are integrating over the entire area. Is it clear to everyone?
Yes, sir.
Isn't it? So remember, whenever we are doing any calculation, when things are varying, what we do? We assume the small element and then we integrate. Yes or no?
Yes, sir.
Same concept we are using here. So we are starting with a point source here, and this point source will be integrated. This DA1 will be integrated over A later on. Make sense to everyone? Is it clear why
Yes,
we have
sir.
taken this DA1 and why we have taken here A2 and why this unit radius, why hemisphere? All these questions are clear to everyone? Hello?
Sir, I got everything, but I'm not will it be mentioned in the question that it is for hemisphere, or we assume?
Don't jump to the questions. We are just starting with the concepts. In fact, if these things are clear, then you will able to understand the subsequent analysis. That's what I'm trying to say. Okay.
Sir, I want to the hemisphere one. I was not able to get it correctly. Why we won't use sphere and we are using only hemisphere?
We are using, okay. So see, whatever calculation we do for hemisphere, that multiplied by 2 will be the answer for the entire surface. That's it.
Yeah, that is true.
So we are calculating for the hemisphere. We could have calculated for the complete sphere also. Doesn't matter, isn't it? We will calculate for the hemisphere, but when we wanted to find out for the entire surface, it will be just multiplied by 2. That's it. Nothing more than that. Okay, all right.
Sir, means you are saying that if we do for sphere, it will be the result for hemisphere into 2.
Yes. Okay. All right. Now the another interesting thing. Okay, so we are saying that consider the hemispherical surface. Okay, now assume that this A2 was a very small surface here, but let's assume that this A2 itself is a surface like a hemisphere. Let's say this entire surface is A2. So this entire surface shown by a red is A2. And I am having another surface DA1 here. So what will be the solid angle subtended by A2 at DA1? the solid angle subtended by A2 at dA1 will be 2 pi. Isn't it?
Yeah, half of 4 pi, 2 pi, yes, sir.
Correct. 2 pi will be the solid angle. Again, it should be actually 2 pi by r square, but we are assuming that it is at a unit radius, isn't it? So that comes out to be 2 pi. Correct. Another interesting thing to note down is this dA1 is at the center here. But if I move this dA1 anywhere on this flat surface at the bottom, anywhere at this flat surface at the bottom, still my solid angle subtended by A2 at dA1 will be 2 pi.
Yes, sir. Yes, sir.
Isn't it?
Hmm.
Correct? Is it clear to everyone? Now another reason why hemisphere is used and not a sphere is used is clear here. You can see, can I have a two surfaces? See, if I wanted to take account the impact of having the entire surface surrounded, that means the dA1 will be encapsulated by A2, isn't it? Then and then only the entire picture is important, isn't it? Does it make sense what I'm trying to say? So in this case, what we have done? In this case, we have done that this surface dA1 is exactly located on this flat surface at the bottom, isn't it? But can I have a situation where this entire surface is this A2 is encapsulating completely a dA1? That means this A2 is a spherical surface and inside that dA1 is there. Can I have this type of situations? Yes,
So
or
we
no?
can have what
We can have such situations in a some specific cases, like if you are looking at nuclear reactor, or if you are looking at, you know, the boiler, isn't it? Boiler type, not exactly the spherical, but it will be completely encapsulated. Is it clear to everyone?
Yes, sir.
But having a perfect sphere encapsulated another surface will not be there most of the time. Do you agree? So if you look at the boiler, how it is in case of boiler, it will be something like this. You are having a boiler like this, isn't it? Inside you will have some tubes here, isn't it? Inside you are having some tubes. You will have a refractory walls here, isn't it? So it's not perfectly sphere, even though these tubes are completely encapsulated here, isn't it? Some fire will be there, coal burning will be there, isn't it? But it is, this entire surface is not spherical. It is, even though these are encapsulated completely, but it's not spherical. Clear? Isn't it? Does it make sense to everyone?
Spherical, completely spherical, or like somewhat portion is left? Are you saying like that?
So I am saying, can we have a situation something like this? In a practical cases, can we have a situation like this?
Then there is no meaning of the inner circle.
Then there is no, then I am saying this entire circle is encapsulating this dA1. Can I have this type of situation in a practical applications?
No.
Very rare, na?
No.
We will not have, isn't it?
Especially design.
So
In
that is
order
why
to prove
very often we only look at the hemispherical part. Even that is not common. Maximally the surface will be here and you are, you know, trying to find out the solid angle, something like this, isn't it? Or maybe similar to this only you will have the situation, isn't it? At max it will be completely encapsulated like this. But these situations we are going to treat slightly different way that you will get to know. Okay, is it clear?
Yes, sir.
I am giving more details here than required because then and then only you will appreciate these concepts later. So as I said, we are, you know, trying to add some more complications in the way we should, you know, look at radiation. Okay. So as I said, this solid angle is very important. This solid angle is very important because how much radiation will be absorbed by another surface is also depends on, it does not depends completely on how much radiation emitted by a particular surface, but also how much is the solid angle, isn't it? So for instance, the question here is how much radiation absorbed on the surface A2. It not only depends on how much radiation is emitted by dA1, but also what is the solid angle subtended by A2 at dA1, isn't it? Correct. That's why solid angle we are trying to look at. Is it clear? Does it make sense to everyone?
Yes, sir.
Okay, now let's try to derive it. What we are interested in? We are interested in finding out the, how much is the time? Sorry. Okay. How much? Okay, so let's look at the derivation. So what we are interested in? We are interested in finding out the hemispherical spectral emissive power of a black body. So we are starting with a black body. Okay, we are starting with a black body for a simplicity, but later on you will see that we will digress from the black body. We will.
Sir, I want to ask you, sir, what is black body? Like I don't like. I listened this many times, black body, but I don't know what is exactly.
So black body is a body which absorb all the radiations. Another interesting property of the black body is its emissivity and absorptivity is 1. Okay, so that is a standard used for quantifying the radiation. It's a standard used. Okay, is it clear? Since all the radiation are absorbed by the black body, it appears black. That's why this typical word is given as a black body. But what actual meaning is, it absorbs all the radiations. So absorptivity is 1 and also emissivity is 1. Is it clear, Achintya?
Yes, sir. Yes, sir. It is clear.
Okay. Okay.
Sun can be nearly called as a black body. Sun.
Yes.
Stars.
Yes. Yes.
Nearly.
Yes. Nearly. Yes. All right. Okay. So consider. Okay. So let's derive this entire thing. So again, let's consider a differential area dA1. Okay. And so the solid angle subtended by differential area dA through which the radiation emitted from the dA1 passes. Okay, so let's say dA1 is the actual surface. The normal to the dA1 we have drawn as shown here. This is the normal direction, isn't it? Now we are interested in finding the solid angle dA in this another direction here. Okay. So how we can calculate this? So just by looking at the geometry itself, spherical geometry we have to consider. Just by looking at the spherical geometry, we can find out that this width will be r sin psi d phi, whereas this another breadth here will be r d psi, where psi is nothing but the zenith angle and phi is the azimuthal angle. Okay, r is the radius, n is the normal direction. All right. Now in this case, what we are doing? This is the, let's say, a surface area dA1 is there. Okay, so its projection in this angle phi we are trying to find out. Its projection in this direction we are trying to find out. So this dA1, the normal direction is n, but we might have another body here. Isn't it? So in that case, the projection of dA in this direction is important. If I'm having another body here, then in this direction will be important, isn't it? So right now we are not considering it. We are considering only a generalized case. We are saying that any other direction, any other angle phi, if you wanted to calculate the projection of dA1, which will be intercepted as a solid angle by another body, that we are trying to calculate here. So since in this calculation, since this body dA1 is going to emit in all the hemispherical, area, so we have to find out this solid angle on the hemisphere. That's why I have drawn a part of the hemisphere. Is it clear to everyone? Is it clear to everyone now?
Yes.
So that's why I have spent so much time in explaining there why hemisphere is important. Okay. So this hemisphere we have drawn because I can take this body, this receiving body anywhere, but the only hemisphere I have to, consider, isn't it? So projection of this body, which will be intercepted by another body, that's what is going to give me a solid angle, isn't it? So that's why any angle I am taking psi, where I am trying to find out this solid angle. Is it clear to everyone? Does it make sense? Hello?
Yes, sir.
Sir, can you explain that point again? The why we take hemisphere? That point one more time.
Any body, if you take it, it is going to emit in all direction, isn't it? So that means the spherical surface is what important. In all the spherical direction, the emissions will be there. But very often you either have the receiving body, in the upper half or the lower half, isn't it? You will not have the body which is, receiving the radiation, which is not, you will not have a body which will completely encompass inside the sphere. So even though you do the calculation only for the hemisphere, that itself will be sufficient for your, calculations, isn't it? You don't need to consider this entire sphere. That is the reason why most of these quantities are defined in terms of hemisphere. Is it clear, Achintya?
Yes, sir. Yes, sir. Yes.
Okay. All right. So now in this case, just from the spherical, coordinates, from the spherical coordinates, this width is going to be r sin psi d phi, whereas this breadth will be r d psi, isn't it? Again, as I said, the solid angle is defined by what? The solid angle is defined by dA by r square, isn't it? dA by r square, that's what we are defining the solid angle. What will be dA in this case? dA in this case will be this width multiplied by this width multiplied by this width multiplied by breadth, isn't it? So r sin psi d phi into r d psi will give you the area. So that becomes r square sin psi d phi, isn't it? And if you put it in this equation divided by r square, you get a differential solid angle dw as d omega as sin psi d phi. Is it clear to everyone?
Yes, yes, sir.
Now another concept comes into the picture. Another concept is a intensity. So intensity of the radiation is defined as the radiant flux passing in the specified direction per unit solid angle. So it is nothing but d Eb lambda by d omega, isn't it? So emissive power per unit solid angle is nothing but the intensity. Is it clear to everyone? Is it clear to everyone? And this is denoted by I. The unit is watt per meter square. So watt per meter square is the unit of emissive power per unit solid angle. That means per unit stereo. By a solid angle. Is it clear to everyone? Does it make sense to everyone?
Yes, sir.
So in this case, let's start with the spectral intensity, spectral radiation intensity of the radiation. So spectral intensity of the radiation for a black body will be given by what? I B lambda. Here B denotes the black body, lambda denotes the wavelength. So IB lambda is nothing but the spectral intensity of the radiation for a black body. So that will be given by what? D EB lambda divided by DW, D omega, isn't it? So in this case, EB lambda is nothing but the spectral emissive power of a black body that I can directly obtain by rearranging this equation. So I can have IB lambda d omega integrated over the angle that will give me the spectral emissive power of a black body. Do you all agree? Yes or no?
Yes, sir. Yes, sir.
Now, is there any question? So this is just a definition of the spectral intensity. Now from this definition of the spectral intensity, we are trying to calculate the spectral emissive power of a black body. So spectral emissive power of a black body will be the integration of IB lambda, which is nothing but the spectral intensity of the radiation multiplied by d omega, and this is integrated over the solid angle. Now the solid angle d omega we have already obtained as sin psi d psi d phi. Isn't it? So that we can put it here, sin psi d psi d phi. Now in this particular case, we are talking about the hemisphere. So in this particular hemisphere, the psi is varying between what? Psi is varying between 0 to pi by 2, isn't it? Psi is varying between 0 to pi by 2, whereas phi is varying between what? 0 to 2 pi. Yes or no? So see, I am just drawing it so that you all will appreciate why I am saying this. So this psi will vary over the entire range here up to this. So it is varying between 0 to 2 pi. Isn't it? Whereas this phi will vary between 0 to pi by 2.
Yes, sir.
And if I vary these two, I am going to encompass the entire hemisphere. Do you all agree?
Yes, sir.
Isn't it? Correct. So that is why I started with this differential surface area here. Isn't it? This differential surface area I have taken here, and this differential area I have taken here. And now I am trying to account this entire hemisphere. Entire hemisphere. Okay. All right. So that's why this dw is nothing, this d omega is nothing but what? Sin psi d phi. Here psi is varying between 0 to pi by 2, whereas phi is varying between 0 to 2 pi. So that's what we have done here. 0 to 2 pi, this is phi is varying, and 0 to pi by 2 psi is varying. Okay. So equation 2 we have obtained for the spectral intensity of the black body. Sorry, we have obtained for the emissive power of the black body. Spectral emissive power of the black body. This is what the expression, spectral emissive power of a black body. So now, in this particular figure, this particular surface, the normal direction of the surface is what? N. Correct? So normal direction of the surface is N. But we are interested in finding out the radiation in some other direction with the angle phi, with the solid angle, isn't it? So it's not a normal direction. So there is something called as a Beer-Lambert law. This Beer-Lambert law says that the intensity of the radiation you can find out in any direction if you know the intensity of the radiation in a normal direction. Is it clear to everyone? So intensity of the normal direction multiplied by cos theta will give you the intensity in any direction. So that's what we are trying to do. So here phi is the angle where we are interested in, isn't it? This psi is the angle we are looking at, isn't it? So that means from the Beer-Lambert law, the spectral intensity in the direction of the solid angle, that will be IB lambda, will be given by spectral intensity in the normal direction. So that will be INB lambda into cos psi. Does it make sense to everyone? Hello?
Sir, is there any derivation kind of
This
thing
is a
like
law.
that?
This is the law given by B.S. Lamberts. This is a very famous law. This you might have done it in your physics also.
Yes, sir, but like I'm asking why cos phi term? It is a law like
Okay, so that is
next.
clear from here. You are looking at this normal direction. You are finding out here somewhere. So this angle is psi, isn't it? So in this direction, if you wanted to see, most of the radiation will be, moving in a normal direction, but you are trying to find out here, isn't it? So intensity in this direction will be given by this intensity in the normal direction into a cos psi. Is it clear? Not clear?
Yes, sir. Yes, sir. Yes, sir. The component which
Component,
is
yes, you are
along.
trying to find out the component in this direction. Yes. Is it clear to everyone? Hello? Okay, so this is the Lambert's law. So Lambert's law says the intensity in any direction can be obtained in terms of intensity in a normal direction multiplied by cos psi. So we can plug in here. We have plugged in this part here. Now INB lambda is a constant term that we have taken out here. So 2 pi. So again, if we integrate between 0 to 2 pi, d phi is varying. Remember, all these terms are with respect to psi. Only this d phi is the separate term. So we can integrate d phi separately. So that will give us the 2 pi. So we will have 2 pi coming out. Integral 0 to pi by 2, and this INB lambda, this will also come out because this is a constant term, and whatever the remaining terms are cos psi, sin psi, d psi, isn't it? So integration of this entire term comes out to be 1 by 2. Is it clear? Cos psi, sin psi, d psi integration between 0 to pi by 2 comes out to be 1 by 2. Is it clear to everyone? Hello?
Yes, sir. Yes.
So ultimately what we get is EB lambda. EB lambda is nothing but the emissive power, spectral emissive power of a black body, which is given as pi times spectral intensity in a normal direction. So this EB lambda is nothing but what? EB lambda is nothing but the hemispherical spectral emissive power. This word is very important. But if I say total emissive power, total spectral emissive power, that will be 2 pi into INB lambda, isn't it? Make sense? But we are only talking about the spectral hemispherical spectral emissive power of a black body is pi times the spectral intensity. Pi times the spectral intensity. That is what we have proven in equation number 3. So now this we can get rid of this word spectral. This spectral we can get rid how? By integrating this EB lambda over 0 to lambda 0 to infinity, isn't it? Because this wavelengths will be in the range 0 to infinity, so we can integrate spectral emissive power over the wavelength varying between 0 to infinity. That will give you a total emissive power. Again, that total emissive power will be for what? Hemispherical. Total hemispherical emissive power of the black body will be given by 0 to infinity EB lambda d lambda. So we can put this here. So pi INB lambda d lambda. So what we are going to get is pi NB. So this integration of INB lambda d lambda 0 to infinity, this term is given as INB. So it is nothing but pi times total hemispherical emissive power of a black body is pi times the total intensity of the radiation in a normal direction. Is it clear to everyone? Hello?
Yes, sir.
Okay. So now let's extend these concepts little bit more on finding the net radiative heat transfer between the two bodies. So what is the time? 45. Okay. So let's find out the net radiation heat transfer between two bodies. So consider two bodies. Again, both the bodies dA1 and dA2 we are considering, and assuming that both these differential bodies dA1 and dA2 are black bodies, and these are separated by a distance L, and the DA1 is making an angle of beta 1 with the normal, whereas DA2 is making an angle of beta 2 with the normal. Is it clear to everyone? So remember, up to this we have not at all looked at the other body here. We have just taken one body and we have tried to find out what will be the solid angle. Then we have tried to find out the concept of this, how this emissive power will be related to the intensity of the radiation in a normal direction. Now we are extending these ideas for calculating the net radiation heat transfer between two bodies. Net radiation heat transfer between two bodies. Again, we have taken a differential area DA1 and DA2. Both these areas we have taken as a differential area and not the complete area, because the complete area might have a their solid angle will not be exactly conical like this, isn't it? It depends on the surface area, so that you can integrate over the DA1 or DA2 to get the complete picture. But since the surface area will be varying, you will be calculating for the elements first and then you will be integrating over the area. Is it clear? Does it make sense to everyone? Hello?
Yes, sir.
Okay. Sorry. So in this case, now let's look at the calculation. So intensity of radiation emitted by DA1 in the direction of DA2. So we are interested in what will be the intensity of the radiation emitted by DA1 in the direction of DA2. So in the direction of DA2 will be given by what? This will be given as IN. IN will be nothing but what? The radiation intensity of the radiation in the normal direction multiplied by cos beta 1. So this beta 1 is the angle between this. This is the normal direction. In this direction, I will have a IN. Correct. I will have a IN in this direction. IN. Okay. So this IN multiplied by cos beta 1 will be the intensity radiated in this direction. Do you agree?
Yes, sir.
Now, what this IN is? Remember, in the last slide, we have defined this IN as what? This INB is nothing but what? EB divided by pi. Correct? Yes or no? INB is nothing but what? EB divided by pi. So that's what we have put. EB divided by pi is, we have replaced the IN into cos beta. What is EB? Is the emissive power of a black body. So that is given as sigma T raised to power 4. So sigma T raised to power 4 divided by pi into cos beta. So this is IB. This is the intensity of the radiation emitted by DA1 in the direction of DA2. That's what we have calculated. Okay. Now the solid angle, now it in addition to the intensity, it also depends on the solid angle, how much radiation is received by DA2. How much radiation is received by DA2 depends on what solid angle is subtended by DA2 at DA1. Isn't it? So solid angle subtended by DA2 at DA1 will be given by what? It depends on, it is given by what? It given by DA2. This is the area. And its projection along this direction will be what? Cos beta 2. Correct? And since per unit area length square we have to use, so that L square is coming in. Remember, solid angle we have defined dA by R square, isn't it? Per unit length, square of the length. Correct? Is it clear? Hello?
Yes, sir. Yes, sir. It's clear.
So now this solid angle also we have calculated, and now IB into this dW solid angle into dA1 will be the rate at which the radiation emitted by dA1 flowing towards dA2. Do you all agree? Remember what was the equation? IB into dW, that will give me EB lambda into area, that will be the total amount of heat transfer in that direction, isn't it? So that's what we have written here. IB into d omega into dA1 will be the rate at which the radiation emitted by dA1 flowing towards dA2. Make sense?
Yes, sir.
Now let's put all these terms. So IB we have already calculated, sigma T raised to power 4 by cos beta 1 into the solid angle is dA2 divided by cos beta 2 by L2, and this dA1 is multiplied as it is. We rearrange the term. So after rearranging, what we get? Cos beta 1 cos beta 2 dA2 divided by pi L square sigma T1 raised to power 4 dA1. So this is the rate at which the radiation emitted by dA1 flowing towards dA2. Flowing towards dA2. Correct? So this can be obtained, this entire bracket we can represent as dF12. dF12. So here dF12 is nothing but what? F12 is nothing but a shape factor, view factor, or a component factor of dA1 with respect to 2. So this giving me the information that how much is the amount of radiation emitted from dA1 will move towards dA2. That's what information it is giving, isn't it? And that information is very important because that defines how much radiation it can intercept, isn't it? Similarly, we can do the same calculation for dA2. We have done for dA1. For dA2, what will be the calculation? For dA2, again we can have the calculation, so that will be cos beta 1 cos beta 2 dA1 pi L square sigma T2 raised to the power 4 dA2. This will be the calculation for the how much amount of radiation emitted from dA2 will move towards dA1. Correct? Again, this we can represent using the shape factor, component factor. So this is represented as dF21. Again, we have kept it as a differential because these are calculated for the differential surface area. Remember, here we have assumed this differential surface area. We have not assumed the complete surface area. That's why these shape factors are also calculated as in terms of differential. Does it make sense to everyone?
Yes, sir.
So dF21 is what we have obtained here. Okay. So now what will be the net radiative heat transfer dQ12 between dA1 and dA2? Will be the difference between these two factors. Do you agree?
Yes, sir.
Remember,
Yes.
this factor is what? This entire thing is nothing but what? This is the amount of radiative energy from dA1 which is flowing towards dA2. This is nothing but what? The amount of radiative heat flux emitted by dA2 moving towards dA1. And difference between these two will be the net radiative heat exchange between 1 and 2, dA1 and dA2. So that is given as dQ12. So dQ12 will be given by these two difference of both these terms. So after taking the difference, what we get? Sigma cos beta 1 cos beta 2 dA1 dA2 divided by pi L square in the bracket T1 raised to the power 4 minus T2 raised to the power 4. So net radiative heat transfer dQ12. Now this entire thing we can represent in both ways. Either we can have dF12 into dA1. So this bracket is nothing but dF12, remember, into dA1. Similarly, we can represent this as dF21 into dA2. And this term is common. This term is common in both. Isn't it? Does it make sense?
Yes, sir.
So this gives a very interesting reciprocal relationship between the geometries, and this is something, it's a reciprocal relationship between the shape factors. So what this is giving is the shape factor of one surface over the other multiplied by its corresponding area is same as shape factor of the other surface with respect to the first one into corresponding area. So remember here F12 into dA1 is same as dF21 into dA2. This is a reciprocal relation. In fact, we will see much more detail later on this. But the interesting point to note down here is now the net rate of heat transfer also accounting a additional factor like this. Can you see the point? Which we were not taking in the consideration earlier. Yes or no? Remember earlier we said that the net radiation heat transfer between the bodies will be directly given by this sigma into T1 raised to power 4 minus T2 raised to power 4. That's it. Difference between that. But this shape factor also important to calculate the actual heat transfer between the bodies. Correct?
Yes, sir.
So was that relation correct, which we studied earlier?
No. So that relation is just to give you a glimpse of that. So see what we have done earlier is this body is there and this body is there. Okay. The emission from this body will be given by emission from this body, let's say body 1. So emission from this body will be given as sigma T raised to power 4. Emission from this body 2 will be given as sigma T2 raised to the power 4. But if I wanted to find out the radiation heat exchange between these two bodies, if I am trying to find out radiation heat exchange between these two bodies, it's not this. It's not this.
Sir, if these two bodies are only there and there is vacuum and nothing is there except this and they are very far apart, then this is valid.
In that case, this is valid, correct. But this equation is a much more simplified case, but actual case is this. Is it clear?
Yes, sir, clear.
Okay, all right. So can you see the point that we are moving from idealistic, representation to more realistic representation? These are slightly more complicated. Don't follow these things from the book. This entire description which is there in these slides are not from the book. In the book, things are little bit more complex. You'll not be able to appreciate these concepts if you look at these things in the book. Is it clear? Does it make sense to everyone what we have done? Yes. So now, so far we are talking about only the differential surface area. That's why the corresponding shape factor or view factor we have represented in terms of differentials. But we can integrate this equation. Remember, this is dQ12. So this is nothing but the heat transfer between the differential surface areas. But if I wanted to find out the heat transfer between the entire surface area, A1 and A2, isn't it? In that case, what I have to do? I have to integrate this entire thing with respect to A1 and A2. Do you all agree? Do you all agree or not? So that's what we have done. The two finite surfaces dQ12 is integrated over the surface A1 and A2. So Q12 will be integrated A1 and A2. This is what we are going to get. This is a constant term, but this term will depends on the area. So this we have kept it inside. Now we are defining F12 as 1 by capital A1, this entire integral. So with that, we can represent this as Q12 is F12 A1 sigma T1 raised to power 4 minus T2 raised to power 4. So this equation is what we are going to use regularly now onwards. Now onwards, we are going to use this equation regularly. Okay. So net radiative heat transfer between two bodies not only depends on the temperature difference and their power to the power raised to the power 4, but also on the corresponding shape factor. And which shape factor I should select? I should select F12. If I select F12, in that case, it should be multiplied by A1. If I'm selecting F21, in that case, it should be multiplied by A2. There's a small difference. Okay. Another simplification of this equation is, let's say one of the area is tiny. Let's say area A1 is very small. In that case, you don't require integration over area A1 and you directly get this equation. So you are integrating over area A2 only, and A1 you are taking out as it is, as a constant value. So then F12 will be defined slightly different way. Is it clear to everyone? Does it make sense? Hello? It's not clear, everyone? Hello? Not clear?
Yes, sir, it's clear.
Slightly complex. These analyses are slightly difficult, but you know, if you go through today's lecture carefully and the slides carefully, I am damn sure you will appreciate. Okay. And I have done it in a much more simpler way compared to what is there in the book. Okay. So if you follow the book, you will get lost somewhere, but these are much more simpler than that. Okay, so we will stop here. We will have a regular class tomorrow 9:30 again, and we will continue on this. One more thing is, I think in the next week we will not have a tutorial. Maybe that tutorial we have already done on the previous Sunday, isn't it? But if some more classes are required later on for the tutorial, we will cover in the regular classes.
So sir, the quiz, CL 251 quiz, which will be on 21 March. What is the timing of the quiz? Timing?
Timing so far it is 9:30 to 10:30, but I have to see whether I can get a big lecture hall complex available at that time or not. Okay, so I will try to book it today. If I am able to get it that timing, then we will have this timing. Otherwise, we will have to see. Okay. So if I get remember we are having almost 200 students, so we require a big size lecture hall complex for conducting the offline quiz, isn't it?
And sir, it is an offline quiz, so we have to take our laptops in the.
No laptop is allowed. You bring a book or you take a printout of whatever the notes I have given. No laptop is allowed offline, so it will be only open book and open notes, not open everything. Laptop means you will use the internet also, isn't it?
No, so like I was saying that the pattern would be the same, that like in Moodle we go and we.
No, pattern will be offline. It will be a regular offline examination. You will get the question where you will have to solve, write all the answers on a the answer script provided. So it is proper offline examination. It will not have a you will in an online thing you only need to enter the answers. It will not be like that. Here everything you have to write down stepwise manner. Okay.
Sir, and the syllabus will be complete till now.
Syllabus will be whatever we have covered, whatever we will cover till the Monday, tomorrow. Tomorrow we will have a last class, isn't it? Last class in the sense before the quiz, not the last class. So I think I will require 2-3 more lectures. So I think one or two lectures I will take on radiation, and 1 or 2 lectures I will take on heat transfer equipment, and that's it. So how many classes we are getting after this? 3-4 classes we are getting. So maximum 4 classes I require, maximum. Whether we will get the 4 classes.
Yes, sir, I think there are 4.
Okay. So that should be okay, and 4 classes plus 2 quiz.
Quiz will be in April, second one, na?
Second quiz will be in the April. Yes, last quiz will be in the April.
So that will give the space for 4 classes.
Okay, all right. Thank you so much, and thank you so much for coming on Sunday. And I'm really sorry for asking you to come on Sunday. Okay, thank you so much.